In 1971, physicist Claude Lovelace published a remarkable claim that the universe has 26 dimensions of space and time. This is one of the most extraordinary predictions of string theory.
So where exactly do these dimensions come from?
In this video, I would like to give you a flavor of how these extra 26 dimensions come about.
We will focus on a theory called bosonic string theory, which is the oldest and the simplest. The idea will be to build a special object called the partition function, which roughly encodes the probability of a string shaking about and coming back to its original state. By construction, the partition function must have a special symmetry called modular invariance, and we will see why this symmetry is only possible when the function has 26 dimensions to live in. String theory describes the basic components of nature as one-dimensional strings. They can be open strings or closed loops, and vibrate at different frequencies. These different frequencies create different particles, such as the photon, the graviton, or the gluon. The vibration of each string can be decomposed into different modes. These modes are numbered by how many times the string self-intersects. Each mode of a vibrating string behaves essentially like a harmonic oscillator, going up and down in the same motion as would a weight tied to a spring. In the quantum world, the harmonic oscillator obeys the Schrödinger equation, where psi is the wave function, a complex valued function such that multiplied by its complex conjugate, it would give a probability density determining the position. I is the square root of -1, and En is a possible energy. Solving the Schrödinger equation also yields how the initial state of the wave function evolves in time. Energy is directly proportional to the frequency and can only occur in discrete levels. Energy is quantized by a positive integer n. When n equals 0, it is called the ground state energy. These energies will become important when we build the partition function later on. To build the partition function, let's think about what happens when the string moves, or shakes, and changes, and then returns to its original state. As the string moves upward in the time direction, it traces out a cylinder. The bottom of the cylinder represents the initial state, and the lid represents the final state. If the initial state and the final state are the same thing, then we can identify or glue the bottom and the lid together. The resulting shape is a donut. Mathematically, the amplitude of a string returning to the same state can be calculated from the time evolution equation, and it yields e to the minus I ent. If we now add these amplitudes over all possible energies, we obtain the partition function. The partition function contains information about how the string evolves and comes back. We can already see how this function must be symmetric. Let's say that the string returns to the same state after 1 unit of time. That means that the partition function must be invariant under the transformation t goes to t plus 1. It is this type of symmetry that will lead us to the dimension restriction d equals 26. To calculate the partition function, let's return to the equation for the energies. Plugging this into our formula, we obtain that for each mode, the partition function is something like this. Each mode is independent, so we take the product of each of their contributions. The frequencies take integer jumps, as they are quantized. So in the exponential, we have to compute the sum of n equals 1 to infinity. This is obviously a divergent sum, and a very difficult thing to work with rigorously. Yet physicists have gone around this by appealing to a very special trick. They consider the Riemann Zeta function and evaluate it for s equals -1 and so obtain -1/12. It is extraordinary that something like this would work, and perhaps we don't really understand yet why it does. One proposal is that we're not interested in the absolute energy of the string, but rather in the difference in energy between the vacuum and the string. Some experimental evidence for this idea has been found in the Casimir effect, where two plates are attracted to each other as there is an energy difference between the outside and the inside. Even if both have infinite energies, their difference is finite and something we can measure. In any case, let's assume this trick works for now, so that the partition function becomes this. Now actually, this is the case for one dimension, but the string can vibrate in d-2 dimensions, where the -2 comes from excluding time and the longitudinal dimension. So the full partition function, as a function of d, is this. Now, we had said earlier that the partition function must be invariant under the translation transformation t goes to t plus 1. So, in order for the partition function not to change, we need the exponent in the first factor to be a multiple of 2 pi. We can set d-2/24 equals 1, and it follows that d equals 26. Technically, we had only showed that d-2/24 is an integer. But hey, it's a start. This at least gives us some intuition of how the dimension restriction can come about. Let's summarize what we did. We said that strings can move, vibrate, and change state. The probability of returning is encoded in the partition function. The partition function is invariant under time return symmetries. We used the quantum harmonic oscillator to evaluate the energies in the partition function. The Riemann Zeta function trick allowed us to get around a divergent sum. Finally, we obtained that the partition function had an exponent of d-2/24, which by the time invariant restriction gave us d equals 26. Firstly, we only considered bosonic strings. If we included also fermions, particles of half spin, then we would get a different dimension restriction, d equals 10. Secondly, the parameter t is not actually time, but the ratio of lattice coordinates generating the torus. It's more like imaginary time and has a fully complex value. Finally, the partition function has actually 3 parts. The contribution of waves traveling left, those waves traveling right, and the contribution of the string moving its center of mass. This makes the partition function into what is known as a modular form, which is invariant under the special linear group, the transformations that preserve the area of the torus. This is useful as a two-dimensional generalization of preserving proper time in special relativity. Modular forms have connections with number theory, monstrous moonshine, and other gems of mathematics.